When you see a rocket taking off for the first time, it's a mind-blowing experience, just the size of a skyscraper. Suddenly you're watching this thing take off and fly into the sky. We're putting these very valuable payloads and putting people on top of these things. It's incredible to watch. A sonic boom can be extremely loud. The sonic booms from the Falcon 9 were well over 100 dB, no matter what metric you're looking at. And the X-59, NASA's demonstrator, those are expected to be down much closer to like the sound of like a car door closing across the street. It might seem like kind of crazy for me to spend the next 4 or 5 years of my life working on simulating a Mars parachute deployment. If it doesn't go exactly right, we just wasted, $10 billion on a Mars mission. There is no better time to get into engineering, and especially aerospace engineering. There is so much opportunity going on right now, from sustainable aviation to the commercialization of space to sending the first people back to the moon in 50 years. It's all happening right now. This is a new space age, and there's tons of engineering to be done.
Welcome to SEL Podcast, filmed in the MD Acoustics Anechoic Chamber in beautiful Gilbert, Arizona. Today, we are joined by Tagg Durrant, a Stanford Aero and Aerospace Engineering PhD student who's already worked with the likes of NASA, Sierra Space, and Farhat Research Group. Each episode, we bring you compelling conversations, practical advice, and illuminating stories from the minds of industry leaders, educators, innovators, and visionaries who are shaping the world one idea at a time.
Welcome, everybody, to Sound Cave Labs podcast. Today, we're coming to you from our anechoic chamber here in the labs. I'm your host, Robert Pearson, and I've got
Mike Dickerson
and
Samuel Horde.
And today on the podcast, we've got Tagg Durrant. Tagg did his undergraduate at BYU, where he worked on the QUESST Supersonic Technology, reentry sonic boom with SpaceX Falcon 9, and he worked at Langley Research Center. Right now, he's a Stanford PhD student, where he works on computational aerospace engineering. Tagg, how are you doing today? Thanks for being here.
Doing great. Thanks for having me on. It's fun to get a chance to chat with you guys.
Yeah, I think it's definitely mutual. We're very excited to have you here, and we're very excited to hear about some of the fun and interesting things you've been doing in the realm of aerospace engineering.
Yeah. I mean, I think the last few years of my career, my academic journey, have been very fun. I've been, we were talking before, I was very fortunate to get all the opportunities that I have to work with some really cool acoustics projects now here at Stanford doing aerospace engineering. So always happy to chat about things in aerospace. It's my passion. It's what I love doing.
I had just a question for you, actually. So I grew up outside of Houston, and I saw spaceships all the time. I went there every summer. For a little while, we lived near Cape Canaveral. We saw launches there. So I have some experience with how loud they were back in like the 80s and 90s. What got you into this, and what do you hope to accomplish in this field?
I was an undergrad. I knew I wanted to work in aerospace in some manner. So I majored in physics because I loved my high school physics classes. It's something that came naturally to me and I enjoyed working on. And so my freshman year, I just was looking for research groups. And so I tried out with one professor who's working on kind of general relativity stuff. And I realized I wanted to do more on like the engineering side. So I started looking for professors who worked more with like aerospace engineering type projects. And that's when I found Dr. Ken Key, and he invited me to come learn about his lab and then to join his lab. And I initially started working on the Sonic Booms project, but then when he had the rocket launch stuff that was picking up speed too, I was like, hey, sign me up. I want to go measure some rocket launches, and apply the same knowledge to another field. And so, yeah, that got me very into aerospace. I already knew it's what I wanted to do, but then I started to, find my love for designing things, that are pushing our boundaries of technology and helping us explore new parts of our solar system and deep space. And yeah, I think for me, it was just that interest turned into a full-on career passion. And it's something that, is driving my entire career now, because I see how much potential there is in this industry right now. And, we have so many new rockets going off. We have a whole new space economy that's taking off right now. It's a really exciting time to be a part of it.
When you're in college and you're in an acoustics program, you're exposed to all types of noise sources. Some, for me, it was music and guitars and all fun things like that. But you were telling me, like, Dr. Kent Gee, what did you guys do out there? You guys went out to, the Bonneville Flats?
Yeah, we went to the Salt Flats.
Salt Flats.
We did a big balloon experiment where we had balloons that were 2 to 5 feet in diameter with full of welding gases, and we blew them up to look at the Mach stems and the waves coming off of them.
So you worked on, you analyzed this stuff. Talk to us a little bit about your experience on, measurement of really loud noise sources. Like, what are the things that you measured?
Well, I also worked with Dr. Kent Gee. Love him. I'll give him a good shout out. He's doing amazing work. But the measurements I took place, like that I took part in when I was at BYU, were mostly rocket launches, and so they were pretty much all out of Vandenberg Space Force Base. So we would, load up our van at BYU, drive 12, 13 hours down to Lompoc, California, and then we'd spend a day or two, driving all around the Space Force Base there, setting up microphones, setting out our ground stations, close to the rocket, far away from the rocket, medium distance from the rocket. And it would take, a good chunk of time. We had to set up all very precisely, as I'm sure you guys, as you are acousticians, know, getting accurate measurements of sounds is actually really hard, especially when it's something like a rocket that is extremely loud. You have a really high chance of clipping with your microphones. You need to be able to capture the full spectrum. And, the rocket is going to be moving as it goes up. So there's all sorts of challenges that go into it. And to make it probably the hardest challenge is that when you're measuring a rocket launch, you can't be next to the rocket as it's launching. Your systems have to be fully autonomous and start recording themselves, because they'd usually kick us off the base the day before the launch so they can do their final security sweep, because nobody's allowed to be within miles of the rocket as it's going off. So yeah, we had to make sure all of our equipment was working perfectly. We had to know the science behind the sound of the rocket and, the levels we expected to come from it, what frequencies we were aiming for, and, choose the right microphones and equipment that was going to last through, the harsh conditions out there. And then, when it finally came to launch, we were usually watching the rocket launching from 5 to 10 miles away. And I'll tell you, those were some of my favorite experiences in college. Like when you see a rocket taking off for the first time, it just like sends like a chill through your body. It's a mind-blowing experience just to be next to a rocket, see this thing like the size of a skyscraper, and then suddenly you're watching this thing like take off and fly into the sky. It just blows my mind with how much power is behind these rockets and how amazing it is that we are able to produce that much power and then control it. We're putting these very valuable payloads and putting people on top of these things. And then we're shooting off these extremely powerful systems and launching them into space. It's incredible to watch. And the sound too, when you hear the sound, you just feel it shaking you throughout each one of those measurements. Even when you're like 5-10 miles away, you feel those low frequency rumbles of the rocket. It's a crazy experience.
Do you have like a 1-minute synopsis of what the future is of aeroacoustics?
Don't know if I'm like I don't know if I have a specific take on where aeroacoustics itself is going. I think there's some very interesting acoustics problem in the aerospace field, like the ones that I've worked on. I'm sure we're going to talk about sonic booms and rocket launch noise. Those in my mind are going to just continue to get to be bigger and bigger problems and more important problems to solve, as we start seeing airlines try to fly supersonic over land, as we have more rocket launches happening in different places around the world. Those noise problems are going to become very, very significant issues for the aerospace industry to take the leaps that it wants to take in the coming decades.
I could tell you're passionate about it, which is awesome, because I think in the old days actually aren't that old to me, and probably to those who listen who are from, the good old NASA days. I always ask myself this, and people ask us, which is better, computational or to go build and then test fail? Sounds like you're on the side of computational, right? As opposed to, test fail, test fail, test fail. It's probably a lot cheaper.
I will say that as much as I love computer simulations, I'm aware that you can't just simulate things and then go fly. It's never as accurate as real life, and you still have to go through the process of putting all the components together, actually go fly. So it's not like we can replace experimental tests with just computational simulations, but we can supplement them and go faster the better we get at modeling things.
Gotcha.
We can save time and money with those expensive experimental tests and have those tests be better informed if we are better at modeling the problem beforehand.
One thing I just want to know right off the top, and I think a lot of people would want to know, is what's computational aerospace engineering?
Computational aerospace engineering can just mean anything you do that deals with mostly computational modeling with aerospace problems. So for me particularly, what I've been working on is I've done things from multidisciplinary design, analysis, and optimization to my PhD research. I got a NASA fellowship where we're going to be working on simulating Mars parachute deployment. It's really just kind of any computer modeling of an aerospace problem. But there's a bunch of other things you could call it, but I generally just refer to it as computational engineering because that's kind of easy for everyone to understand.
By the way, you said Mars. Can you dive into that a little bit for just a second? What are you going to be looking at?
Yeah, so as I'm sure you know, Mars entry is is a very hard problem. You can't really like go out and just do a little experimental test with landing something on Mars. You spend billions and billions of dollars sending a rover to Mars, and as it gets there, there's about a few minutes of reentry where the entire mission is at stake. And during that time, you also can't communicate with your spacecraft because as it's coming into land, there's a good 30-minute or so delay in communication. And so you can't communicate with your rover. By the time the communication gets back to you, it's already over. And so those few minutes where it's coming in at extremely high speeds and entering the Martian atmosphere, has to perform some very precise maneuvers with, some aero braking, some parachute deployment, and then, eventually landing on the surface. You have no control over that, and your whole mission can go wrong if just one of those parts goes even slightly wrong. So it's a really hard problem. And specifically with the Mars parachute deployment, it's a really difficult fluids problem because you have a spacecraft entering the atmosphere at supersonic speeds, hypersonic, and then it slows down to supersonic. It still has shock waves coming off the body. And those shock waves are then interacting with the parachute behind it. And so to simulate that high-speed flow over a parachute fabric that's super thin, it's flowing over the wind, it's changing shape constantly. It's extremely challenging to model with with computers. And so our research is just going to look into doing better simulations of it so that instead of having to do some really expensive flight tests, we can accurately predict failure modes of these parachutes in a computational setting rather than having to, fly something up in a very high atmosphere or send something to Mars to see if it works.
Yeah, you mentioned that you like to design stuff and that aspect of the engineering side. So I have to ask, what UFO tech do you know that we have and how close are we to having a flying saucer?
I mean, we have some pretty amazing technology, and I'm sure we could design some sort of flying saucer. But anytime that we design something, it's no longer a UFO. Because it's not unidentified. So to make a UFO is kind of counterintuitive, or it's kind of an oxymoron. But I think we are definitely working on making some very cool technology. I'm very excited about the whole eVTOL industry of like electric vertical takeoff and landing aircraft and stuff like that. So there's tons of really cool aerospace concepts that I think are going to revolutionize the way we live our lives next decade.
So to piggyback off of Robert's UFO question, basically a UFO probably doesn't exist because if it did, we'd be hearing sonic booms all over the place unless they have like a black hole that can suck in the sonic boom before it, or time warp that as it's driving, it sucks it back into the time warp.
They might just be an advanced civilization with sonic boom controls, that's for sure. Anything that creates lift and flies faster than the speed of sound will create a sonic boom. So pretty much anything moving faster than Mach 1 is going to create a sonic boom. You can't really avoid it. You can reshape it. You can fly it in different ways. But if we have aliens flying, flying saucers at Mach 5 across our skies and we can't hear them, then obviously they know something we don't.
So I've heard the terms hypersonic and supersonic. I thought they were interchangeable, but I heard you use them like in a very distinct way. What's the difference?
Yeah. So supersonic, well, I'll start from the slowest. The slowest is subsonic. That's anything from like Mach 0, not moving, up to generally about Mach 0.7 is when you would start using the term transonic. Transonic means something that's around the speed of sound. So usually we look at that around Mach 0.7 to 1.2 range. Supersonic means anything above Mach 1, you're going faster than the speed of sound. And then generally hypersonic means Mach 5 or greater. And there's no exact reason. There's nothing that happens specifically at Mach 5 that, is like, this is now completely different. But that is around the speed that you start to have some really intense temperature changes and effects with the gas flowing. You get some really, really big jumps with those shock waves. And so that's why generally you reserve hypersonic for something going Mach 5 or above, so that's like things entering the atmosphere at like, 5, 10, 15, 20, 30 times the speed of sound. We call that hypersonic.
Thanks for explaining that because that could have gone over my head so fast that we had a sonic boom. So
yeah, call me out because I feel like I appreciate when people explain the simplest terms because I'm still someone who I hear a lot of basic terms in my program all the time and don't understand it. And so I appreciate it when people take the time to actually say what these words that they're saying actually mean.
I saw on some of your LinkedIn posts you're doing some predictive modeling of the sound propagation from a sonic boom. How loud is a sonic boom?
So that is the question. A sonic boom can be extremely loud. Like if you think of the ones I measured from the Falcon 9 booster landing, those ones. And again, it depends what metric you're looking at measuring it with. And it's been a couple of years now since I've looked at all the metrics, but I believe that the sonic booms from the Falcon 9 were well over 100 dB, no matter what metric you're looking at. Then the ones from the X-59, NASA's demonstrator aircraft are hoping to fly here in the next year or so. Those are expected to be down much lower, much closer to like the sound of like a car door closing across the street, where you can hear it. It's like a thump, but it's not like a boom that shakes your house. Because if you had a military jet, like say an F-18 fly over your house, going Mach 1.5 or something, that would shake your house. It would sound probably like an explosion, and it would rattle some of your furniture and things. If the NASA's demonstrator aircraft, the QUESST aircraft, flew over your house right now, you'd probably hear it. But hopefully the goal is it wouldn't annoy you, at least significantly. You'd hear it most likely, but it wouldn't rattle and shake your house.
So they have jet aircraft that leave from Mesa Gateway Airport that fly back over towards San Diego, and they go supersonic. When they go over towards Yuma, Arizona, you literally can hear, they're far away. In the wintertime, I can hear the sonic booms. Have no idea how far they are. You can't track them or whatever, but I can hear the low rumble. If we're going to have commercial aircraft flying over the United States that are going supersonic, it's going to be a huge problem. I'm glad that there are people out there that are looking at these problems and looking at ways to solve them.
Absolutely. I think I'm the kind of guy that if a sonic boom happened in my neighborhood here in Sunnyvale right now, I'd probably like run outside and like start like clapping and say that was like so cool, like do more of that. But I'm sure not all my neighbors would have the same reaction, because they'd probably think some bomb went off or something and wouldn't enjoy as much as I would. But I understand that the general public does not want to be hearing, a couple sonic booms a day.
No. So I read some papers about how they were simulating basically different shock waves and also sonic booms, and they'd fly aircraft upside down or in different configurations. Were you in school? Did you guys read any of that kind of paper, or any information on that, or are you aware of anything like that?
As far as like flying the aircraft in specific configurations to get sonic boom?
That's right.
Yeah, and I actually was very familiar with some of the aircraft maneuvers that they would do to produce quieter sonic booms. So I'd talk about one of the test campaigns I worked on a ton in my undergrad, which is the Quiet Supersonic Flight's 2018 test, or QSF-18. And that is one where they flew an F-18 off the coast of Galveston. Okay. And the way they got a quieter sonic boom over the city of Galveston, then they went and surveyed people to figure out how annoyed they were by the sonic booms. They had microphones all over measuring how loud it was. So they took the F-18, flew it several miles off the coast of Galveston, and then they turn inverted, and then they do a dive. And that creates a quieter sonic boom, because it's farther out. It kind of pushes the sonic boom inland. And so you get a much quieter sonic boom that's closer to the levels that you'd expect from NASA's Quiet Supersonic Technology demonstrator. So those ones would be, closer to an average of like 75 or 80 dB rather than like 115 that you get from like an F-18. So
gotcha.
Yeah, those are some maneuvers that definitely were very complicated. I'm not even sure how they figured out how that would produce, the exact sonic boom they're looking for. But yeah, it was much quieter. I think in big part just because they flew it so far off the coast. They weren't flying over the community. They were flying 10, 15 miles off the coast, and doing this inverted dive. And that pushed the sonic boom kind of inland. It was coming much more of a grazing incidence rather than coming from directly overhead. So and so I think the boom shape combined with the propagation distance made it much quieter.
Wouldn't the ground material affect that as well, as far as being over the ocean versus being over land, or hard ground versus soft ground versus water?
The absorption coefficient. Yeah,
absolutely. Yeah. And so we did some work with that, looking at, the different ground plates we needed to measure, the sonic boom in each location. But then, I think I didn't personally look too much into like the effects of like it propagating over water, but all those things definitely come into play, and you have it hitting buildings, going around buildings and stuff. And so all sorts of super, super complicated effects that make it really hard to predict and to measure sonic boom loudness in each location.
Do you find yourself educating a lot of people in terms of like how hard it is? For example, you're talking about the Mars. How much education and how you kind of pitch that? Like, how hard is that for you to kind of pitch those ideas?
It's definitely a challenge. And I think that's one of the hard parts of aerospace engineering, from acoustics to computational engineering to robotics. Like when you start talking about rockets and aerospace, people just kind of tend to get like a glazed look and like, oh, rocket science, I don't know anything about that. And it's just, it's got such a stigma about it that aerospace engineering is impossible to learn. It's just too complicated to understand. And so I think I do have to put a significant amount of effort into using language that helps people realize, hey, this is not something that's impossible to understand. If you just like listen for a minute, if you're a student, if you just apply yourself a little bit, or even you're just an everyday person, like rocket science is actually a lot more approachable than I think most people believe it is, just because it can kind of sound scary from the outside. We use rocket science to describe something that's impossible to learn, but it's really not that way. But you do have to do some education with how difficult some of these problems are that seem simple for sure. Like, it might seem like kind of crazy to spend, for me to spend the next 4 or 5 years of my life working on simulating a Mars parachute deployment that's going to allow, I'm going to simulate this 0.8 seconds of this parachute deploying. I'm going to spend like 4 years on that. That's because that 0.8 seconds, if it doesn't go exactly right, we just wasted, $10 billion on a Mars mission.
It makes it or break it, no pressure.
Yeah. And so like sometimes these little tiny improvements that we make are really significant. And I think that's hard to communicate too. And I think, especially with like the sound stuff, that was always something that I think that blew my mind when I was an undergrad, learning how hard some of these things are to do. I learned about different airlines and NASA working on quieting a jet engine by 0.2 dB over a course of like 3 years and considering it a huge success. Like any little tiny improvement you can make is massive.
Yeah. So do you, on the communication side of this stuff, like how do you communicate? Do you have a podcast? Do you have a newsletter?
Yeah. So communication with aerospace engineers is one of my biggest passions with it, because I really want to make it more accessible to more people and especially inspire more students to not give up on it and to really chase their passion with aerospace engineering. So when I got to Stanford, I met several like-minded students that also love communication and love aerospace. And we started a community, a newsletter, first of all, called The Overview. And what we do on there is we write articles and stories about our experiences that give aerospace engineers the tools, connections, and the knowledge that they need to launch their career in aerospace. Because a lot of times aerospace can seem daunting, it can seem impossible, but we've all realized, we're giving the same advice to a lot of people. And if this advice was just a little more accessible, then aerospace would be a lot more approachable. So we've written articles ourselves. We've interviewed and gotten guest articles from people at different colleges around the country, at MIT, some of my friends over at BYU, at University of Illinois. We've had lots of good co-authors guest authors who have come on and shared some really good stories and some really good technical subjects as well in aerospace. And our goal is to make it so that aerospace students have a way to get that knowledge and get those connections that we were lucky to have, but we wish we had earlier on. So I've been working with, our team at The Overview. There's 4 of us that started and are still working on it. And we've started doing a podcast. We've written newsletter articles. We've got a website up. It's called The Overview. So you can find it at theoverview.org. If you're an aspiring aerospace engineer, definitely go check out theoverview.org and check out our newsletter, watch our podcast episodes. We hope it's a great resource for you. And as for something else that I would like to say, just to like those generally interested in engineering and hopefully, aerospace engineering too, is there's no better time to get into engineering, and especially aerospace engineering. Right now, there is so much opportunity and there's so many world-changing projects that are going on right now, from sustainable aviation to new ways to flying to, new rockets that are making space more accessible to everyday people and to more and more companies, to the commercialization of space, to sending the first people back to the moon in 50 years, to sending people onto Mars for the first time ever, to sending new telescopes into space to explore the deep universe. It's all happening right now. This is a new space age, and there's tons of engineering to be done, tons of acoustics problems that need to be addressed, but tons of just engineering problems in general. So I would definitely encourage anyone who is interested, who has ever thought of aerospace, and working in some kind of space economy. It's a dream job. It's not just a dream. It can definitely be a reality, and there are a lot of good tools out there, and there's a lot of good opportunity for anyone who is motivated and willing to put in the work to get out there and really have a really good career with this.
The $1 million question: Where are you going to be in 5 years? I mean, you got PhD. Where are you going to be? I know you have. Listen, I followed you for a while on LinkedIn. I've seen who hits you up. You got some big companies out there who are hitting you up publicly, so we know that you're well sought after, flat out. And you know what? That's awesome. I think it's awesome that you are a good voice for your generation. Like, honestly, to me personally, you coming on here is awesome, because it's like, I feel like when I was in school, I had minimal resources to help me out. and find like the niche or like whatever I was looking for. And I think you're going to do the exact same. But where are you going to be? You're going to be in 5 years. Do you have that? I mean, do you have any idea, or are you just going to take it as it comes?
I might pay $1 million if you could answer that question for me. But I think that's the exciting part about this, is that I'm not exactly sure I'm going to be in 5 years. That's right about when I'll be graduating and starting my career. And I think for me personally, I want to work in the commercial space industry. I'm getting a PhD, but I think my plan currently isn't to go into academia right away. I think there's a lot of exciting work going on in the space industry, and I want to be a part of that. And so as to which specific company that would be, I'm open to it right now. I'm keeping my eye on the industry and kind of keeping my focus on building my connections and watching how these different companies develop over the years. That's one advantage of doing a PhD, is I have a good 4 more years to just watch how these companies develop and see if they can accomplish the things that they're saying they're going to. So I don't know exactly where I'll be, but I'm looking forward to taking an exciting role and playing a big part in helping lead this next space revolution in the industry.
Thank you, Tagg. We really appreciate you coming on. Everybody, go listen to his podcast, read the newsletter. If you're at all interested, seek it out. Obviously, it's something that's very attainable, and Tagg proved that. And Tagg, you mentioned if you heard a sonic boom, you'd be outside clapping. I picture you out there as a kid when a semi comes by, just like, more, more, more. So hopefully you just always are out there just wanting more of that.
That's awesome.
Thanks for coming on. We really appreciate it.
Well, thank you guys so much for having me. It was a pleasure.
Absolutely.